Hi, welcome to my animation on time dilation. We saw earlier that simultaneity of events depends on the state of motion of the observer. Now we will see how the rate of time also depends on this. Let's start with making a clock. A light flash will bounce up and down in a vacuum between two mirrors. The distance between the mirrors is half a light second, so it will take the flash exactly 1 second to bounce once up and down. And when it hits the bottom mirror, it will trigger the counter at the bottom. So we have a clock. Watch this. That were 10 seconds. Now let's add another clock that moves relative to this one. Let's follow the clock between these points, which are 5 light seconds apart according to me. The clock at the top will move at half the speed of light to the right. And let's first suppose that speeds add up, such that the speed of the flash would be the vector sum of v and light speed. In that case, the light flash would bounce up and down as fast as the one in the clock at rest. And both clocks would remain synchronized. Newton would be delighted, like this. But speeds don't simply add up, and the speed of light is a constant. The flash has to travel over a larger distance in the situation above. It has to bounce up and down and follow the clock itself, all with the same speed as the flash below. The speed for bouncing up and down above is only the square root of c squared minus v squared, and that is smaller than c. So it will take longer for the flash above to bounce up and down. And so the clock above will tick at a slower rate than the one below. Let's see how that goes. Let's follow that clock again over a distance of 5 light seconds as it really goes. The flash above bouncing up and down with a speed of only the square root of c squared minus v squared. As you can see, the clock above was ticking slower. It read 8.66 seconds when it reached point B, to be precise, instead of the 10 seconds registered on my clock. That is time dilation. Time appears to run slower when moving. But did you notice that Newton also seemed a bit thinner while moving? He did, and that is length contraction. We will deal with that later in another animation. Let's now check the distances between the events A and B. For me, there was a space distance of 5 light seconds and a time distance of 10 seconds between them. For Newton, the space distance was 0 because he was always at the origin of his reference frame. And a time distance of 8.66 seconds. Now we will define the space-time interval. Its square is the square of the light speed times the square of the time distance minus the space distance squared. It's the same for both of us. It's 8.66 light seconds. You can check this, bearing in mind that c is 1 in the units we use here. In the next animation, we will show that time dilation is relative. Newton can claim that he was at rest and I was moving, that my clock was running slow, so stay tuned. Thanks for watching. Enjoyed this video? Please like it. Feel free to comment or subscribe to my channel.